And we are live. Hi, ast111x. My name is Frank. And with us tonight is Tom.
Thomas here.
Tom is here. Alex is off enjoying his Thanksgiving drive to back home in Austin, Texas, so he's not going to make it this evening. Let's see. So generally, I think what we're going to do is we'll answer a couple of the questions that are on the discussion board. You can also type in questions on that discussion board as we go along. There's also a chat line that you can type in questions, I believe, on the YouTube Live. And we'll just kind of go for an hour. Tom has a presentation to do. I've got one to do, and we'll just play it kind of loose with the time and see how we go. So let's begin with a couple of the questions that were posted on the discussion board. Tom, you want to take one of those or start one of those?
Sure. One of the questions involved postulating that a planetesimal from another solar system that got ejected somehow might make it to our solar system, and would it be possible for our solar system or our sun to capture that planet? When they say planetesimal, I'm assuming they mean maybe it was small for that solar system, and somehow it achieved escape velocity, and maybe it comes to our system and it's no longer a planetesimal, but a good-sized planet, maybe like perhaps Mars or something like that, maybe even Mercury. And we're saying it'd be really hard to come in just at the exact right speed and the right position to have a good orbital vector that it would start orbiting the sun. Most likely it would be either too fast or too slow at the position that would be required at the speed it was going. So theoretically it's possible, but in practice it's very hard to capture something in an orbit. So Frank, would you like to?
Yeah, just direct captures are hard. That requires a very fine-tuned problem, basically coming in on your speed or coming at the angle that you're coming in at, how close you're going to get. It requires a pretty special set of circumstances to do a direct capture. And as Tom noted, let's say that thing's coming in from the outer solar system. Well, by the time it's falling into our solar system, and by the time it gets to anywhere near the sun, it's already achieved the escape velocity of our solar system. So it's really moving. And I think Tom is right. It might be theoretically possible, but it seems really unlikely. Certainly at first pass, it seems unlikely. You might be able to do some sort of an almost capture, where you slow it down enough so it doesn't go booming out of the solar system, and so it doesn't achieve escape velocity out of our solar system, so it comes back for a second try or a third try, and maybe then it has a better chance of being captured. And whether it would have an impact on our solar system or not depends on the mass, basically, of the object that's coming in. If you're a little tiny asteroid, no, not going to do much. But as Tom mentioned, if you come in as a Mercury or you come in as Mars, yeah, you're going to perturb the planetary orbits. Usually not for the good, right? Because we have a very ordered system. It doesn't take much to perturb an ordered system into something a lot more chaotic on longer time scales. So,
yeah, that would be bad if it were Earth size or Mars size, and tweak this.
It'd be like a pachinko machine again inside the inner solar system as everybody starts competing with one another for space. Yep. So we'd probably get ejected. That's usually what happens in those direct capture scenarios. Is you capture, but another body gets ejected in the ensuing orbital dance that takes place.
Sounds like a pool table shot where one ball hits the other, and one ball gets ejected and the other stays where the other guy was.
That's right. Yep. Okay. Let's see. What else we got?
The other one was on the directions in outer space.
Yeah, directions in outer space. Okay. Let's see. That's got several answers depending on exactly what one means by outer space. And space considered a globe. Okay. Let me start that one off by saying, in general, no matter what, there are several coordinate systems, and all of them can be described in Cartesian coordinates, where you have x, y, and z. So the familiar three directions. You can describe it that way. That's very important to know if you're, for example, wanting to fly a spacecraft to Mars. You want to know the exact position, so you need the x, y, z coordinates of where it is. So you can describe them in that triplet. If it's you're observing something like what we do on Earth, then you can just use two angles. So you can convert from Cartesian coordinate x, y, z into a spherical coordinate system of two angles. Basically an angle around this way and an angle this way. So you can convert back and forth between x, y, z and two angles, assuming you know a distance. And then you can convert back and forth. So it really depends on your purpose. The celestial sphere, for example, is what we use on the spherical angle, whether it's right ascension and declination, or it's horizon angle, and altitude azimuth, which I think Tom might talk about later. So yeah, and then there are a variety of coordinate systems depending on what's most convenient for the problem that you're doing. There are coordinate systems that are centered on Earth. That's your altitude azimuth. There are coordinate systems where the origin is at the sun. There's coordinate systems, there's the galactic coordinate system, there's the supergalactic coordinate system if you're doing faraway galaxies. So all of them establish an origin, and all of them establish basically the x-axis, a direction from which you're going to call the x-axis. So in familiar coordinate systems like what we use here on Earth, or if you have the sun at the center, typically you choose the direction toward the vernal equinox as your x-axis. And then your z-axis is always defined as the direction usually perpendicular to an ecliptic plane or aligned with rotation axes. So, for example, the whole galaxy rotates, and so the z direction is the north galactic pole and the south galactic pole. So rotation generally defines the z direction. You pick where you want your x-axis to point, vernal equinox, and then because you want to have a right-hand coordinate system, that immediately implies the direction of the y-axis, which generally doesn't point anywhere. So you pick two, and the third one is determined. So we pick the two. So yeah, that's kind of what I had to say on coordinate systems. You want to add anything to that, Tom?
Well, yeah, I would say the galactic coordinate system, where you define an angle by looking at the center, towards the center of the galaxy, and we sort of lie in the plane of that galaxy. So if something's above the plane, that's sort of another angle. So it's I believe that's usually denoted by the letter B.
Right.
And yeah, and the angle that you're off from pointing directly at the center, that's usually called L. So you have L and B coordinates.
Right, which is latitude, longitude, right?
Yeah.
B is latitude.
Basically, right.
L is longitude.
And you might see that if you look at all sky maps of different radiation bands, like the Milky Way and the X-ray band, or the a radio band, say the 408 megahertz.
Kind of a curiosity of that system is that the origin is still the sun. And then the preferred direction where you set your x-axis is toward the galactic center. So you might think in something called a galactic coordinate system that you would put the origin at the black hole in the middle of the galaxy, but in fact we don't. You can put the origin wherever you want, and so it's most convenient for us to put it at the center of the sun and then point the direction toward the monster in the middle.
Yeah, I guess that causes a problem, doesn't it, with the epoch you're in as the sun orbits the galaxy.
Yes.
So every once in a while you have to make adjustments.
Yep.
So you might see what epoch you're talking about.
Right, and astronomers tend to, every 40 years or so, have some major updating as things shift around on the coordinates. So one of them, a big one, was the 1950 coordinate system, and then there was a big change in 2000. So it's every 50 years, excuse me. Of course, in real time, you have to correct in real time if you want to find the object you're looking at. So you need to know all those correction terms so you can put it in. But the next big common epoch denominator will be done in 2050.
Yep, that's quite a ways from now. 34 years. Interesting.
I might be around.
Yeah. You never know.
Never know. Okay, I think we got that. So why don't we head into one of the presentations? You want to start off with yours, Tom?
Sure.
I'm going to mute my mic when you get on full screen. And I'll be looking for questions that people are posting while they're watching this.
Okay. F5. Did that come up full screen, Frank?
Not yet, but there might just be a delay.
Let's see.
No, I do not have a screen share yet.
Okay. It says I'm screen sharing.
Screen share and then share the desktop.
Oh, how about now? Is something showing? Screen share. Let me try this again.
Yeah.
Screen share my entire screen. Share. How about now?
I know. Okay. Let me try a test and see if maybe, just so people know, we did test all this before we started. So now all of a sudden we're live and it doesn't work. Let me try a screen share. Let me see what happens. I'm going to screen share my desktop, start screen share, and do you see a screen share, Tom?
Yes, I do.
Okay. Well, how about if we adjust and I'll go, and then we'll see if we can get yours up and going.
Okay. And you said entire screen, right? Not
yeah,
just
I shared the entire desktop.
Okay, mine just says entire screen.
Okay.
I don't have a desktop option.
Okay.
But sure, go ahead.
Okay. Okay, I'll go. So one of the objects we don't talk about much in this course is the big monster in the middle. So that would be the sun. We don't talk a whole lot about the sun. So I want to say, give a little module on El Sol here. And so all cannot live on the piazza, but everyone may enjoy the sun. So we are going to take a journey to the center of the sun, starting from Earth, and we'll make our way back on shorter order. So I just like this art piece here. It's simple. We're going to get in that spaceship there that's shown, and we're going to take a journey to the sun in that spaceship with those lovely space portal holes, so we can see what's going on, along with a full complement of instruments as we go. So as we begin our journey from Earth, the sun, of course, looks like a giant ball of glowing gas, because that's what it is. It's a thermal radiator, and we've studied thermal radiators in this course. So the luminosity is related to the radius and the temperature to the fourth power. And so the total luminosity output of the sun, the total power output, how many joules per second, that's what we call the luminosity of the sun. That's what astronomers call it, is the luminosity. Other people call it total power, right? How many watts come out of the thing. So the sun has a big light bulb that puts out roughly about 10 to the 26 watts, a few times 10 to the 26 watts. That's a lot. So if we could capture and store just 1 second of the sun's luminosity as though we were a type 3 Kardashian civilization, we could meet all of humanity's current energy usages for the next 500,000 years or so. But of course, that's quite a technology, and that's why we're not a type 3 Kardashian civilization yet. We're not even type 1 yet. we're still trying to figure out how to harness that big nuclear reactor in the sky. Because we don't capture much of it. The rest of it disperses out in all directions, right? Because the Earth, and we've done a homework problem like this, right? So you have a little tiny disk of the Earth, and what is the fraction that it captures of the sunlight that it captures from the whole sphere of the sun? And it's pretty small, as you've, I think, worked out in Lab 7. So this is a dual shot. You're taking a look in white light, and then you're taking a look where you take a filter. Typically, that's what astronomers do. You take a filter and you put it in front of the telescope to block out unwanted photons, and this is what's called H-alpha. So this is, you're basically looking at the sun in hydrogen and taking away the rest. So, okay. So most of the energy that comes out of the sun, as we know from thermal radiators, is in the visible. That's where it peaks in wavelength space. And so most of the energy is invisible, but once we leave the protective blanket of Earth's atmosphere, we're going to encounter all kinds of other ones, including this gorgeous picture of the sun in X-ray from a satellite that's up now. It's called New Star, and it's an X-ray observatory. It does other things besides look at the sun, but it can also look at the sun here. So you're looking at the X-ray emission coming off the surface of the sun, and you see kind of like these holes and light booming out of holes. And, we'll cover a little bit about where those holes come from here in a little bit. So as we go, we're going to need some substantial shielding on our spacecraft to present, so we don't get serious radiation burns or other types of particles emanating from the sun. And I like this kind of image because it shows sort of 3 generations of space travel starting from clipper ships from the 1800s in the foreground. To the background there is our current shuttle type technology to get us up into near Earth orbit. And then of course our science fiction compels us to have spaceships that can boogie around from the stars and get in all kinds of mischief. So we sort of have our 3 there. So we know how to take the light from the sun and break it up into its colors. And when we do that, we get, as we've seen before, we've seen this spectrum. You get a continuous spectrum with absorption dark holes poked in it. And from those dark holes in it, we can tell the composition of the sun. So it's mostly hydrogen. That's the most abundant element in the universe. Helium, in fact, that's how helium was discovered. Helium was not discovered on Earth. Helium was discovered as an element by looking at the sun and going, wow, look at these curious lines. What is this? Oh, it must be a new element. Helium, second lightest one, second most abundant element. Not discovered on Earth, discovered in the sun. And then 2% of all the good stuff that we're made out of: carbon, oxygen, iron, sulfur, silicon, etc. That's sort of a very nice picture of the sun there. So we know what the sun is made out of. As we start approaching the sun and we look through the sun through a telescope, you can see that the sun is sort of this churning gas, and it's got a few dark spots, which we call sunspots. Galileo is the first one to measure blemishes on the surface of the sun. Moves, and they move. They don't sit there, they move. Now they look dark, but in actuality, they're blindingly bright. They just look dark because they're just a little bit cooler than the surrounding surfaces around them. The image here shows a sequence of shots over the course of roughly about a week, and you can see the sunspots move from one side of the sun to the other side of the sun, And to give a little bit of sense of scale, the image underneath there shows the approximate size of the Earth relative to a sunspot. Sunspots are way bigger than the Earth as I move across there. Okay. And if we watch those sunspots, as we just did, we saw that time sequence, you'll notice that the sunspots near the equator of the sun circle faster than those at the higher latitudes. And so the sun does not spin like a ball, a rigid ball. It rotates at different rates at different latitudes. This is called differential rotation. So the fastest speeds take place at the equator, and as the image shows there, it's roughly about 25 days, and it gets slower and slower as you get up to either the north or the south rotation axis. So up around like the Arctic Circle or the what would be the Antarctic Circle on the sun, it's about 35 days. So there's a difference of about 10 days between the equator and the pole on where it rotates. And as we continue toward the sun, we're going to notice that there's this increasingly large headwind as we get in. We're battling the solar wind as we get closer to the sun, leave the Earth. And this solar wind is made out of photons, right? It's light from the sun. Protons, which are basically hydrogen atoms. And we got helium nuclei. So those are the two most abundant things that the sun is made out of. And then we get some free electrons flowing outward from the sun as well. So those protons and helium atoms are completely ionized. So they lost all their electrons because it's hot. And those electrons also get pushed out from the sun in the wind. Lovely image here of the sun showing a number of the features that we're going to go through as we take our spaceship through. So we're going to go through the solar wind. We'll talk about coronas. We'll talk about convection zones, chromospheres, photospheres, radiative zones, the core, and then back out. Okay. So this, as we've seen, the solar wind is what helps shape the magnetospheres of planets. We have that lovely quilt that somebody did this year showing a magnetosphere of a planet. And it helps protect the planets. It's like a little cocoon. It's also is what blows off, gives comets their tails when they come on in. They're interacting with the solar wind, and that pushes the material that effectively boils off, those volatiles that boil off, and they interact with the solar wind to give us the tail. The image here shows Mars and Earth. Mars, of course, lost its magnetosphere quite some time ago, and so the solar wind comes impinging pretty close to the surface, whereas Earth is more massive. It's still got an active liquid core, and so we generate a magnetic field, which gives us a nice cocoon from that otherwise pretty damaging solar wind. About 1 million miles above the surface, we enter what is called the corona. And this is the tenuous uppermost layer of the sun's atmosphere. I guess the equivalent on Earth would be something like the exosphere, or maybe the thermosphere as you go in. But it's the outermost layer of the sun. This is an example of what the corona looks like. You can take a shot here. This is during a solar eclipse. That's an image of the moon in front of the sun. So it's not the moon putting it out, but you blacked out the sun. And when you do that, it gives you a chance to see the corona, which otherwise you would not ordinarily be able to see because the sun is so bright. And so you can see that there's a lot of order to that corona. There's a north pole, clearly, a south pole. There's flary stuff, loops going on in the corona as we go through. So the temperature in the corona is about 1 million degrees. It's hot. It's almost as hot as the center of the sun. But you don't feel that heat, though, because the density is so low. So not many particles are going to hit you. So they're moving fast enough to have a temperature of 10 to the 6 that it's not like you're going to stick your hand out there and go, ooh, hot, because there's just not a lot of particles out there. And the corona, being 10 to the 6 degrees, is where most of the X-rays come from. So this is a shot from an earlier generation of X-ray satellites showing different colors here, meaning different temperatures. So anywhere from 2 million degrees to 1 million degrees in different colors, which you can read there on the bottom. And you can see that the sun is sort of this modeled pizza with different parts of the corona emitting at different temperatures, all roughly of order 1 million degrees, but not 1 million degrees everywhere. Some parts a little hotter, some parts a little cooler. As we head into the core of the sun, as you go on in, you will find that the temperature drops from about 1,000,000 degrees out in the corona, as shown by the plot there, and it drops down to about 10,000 degrees in what is called the chromosphere, the color sphere. That's what chromo means. And it will continue to drop down when we get into the photosphere, which is what we see when we look at the sun. We see with our eyes, we see the place where visible light comes out. So X-rays come out of the corona, ultraviolet comes out of the chromosphere, and visible light comes out of the photosphere. Not unlike the layers of an atmosphere that we learned about the Earth, right? We had different layers absorb different layers of radiation, and you get sort of the same phenomena here, although we call it different names: corona, chromosphere, and visible light. So the chromosphere is the primary source of the sun's ultraviolet light. Here is a shot of that ultraviolet light from the sun in this lovely rose-colored feature. Exactly what causes that, we're going to get to in a minute. What causes that structure, those pointy things, those flowing lines, that gives it sort of a flower-like appearance in this shot of ultraviolet in the chromosphere. So as we go into the chromosphere, our compass is going absolutely nuts, indicating that the solar weather is shaped by intense magnetic fields. And on occasion, we get huge magnetic storms, which shoot hot gases out into space. This is an example of a calculation. The image here is shown as an example of a calculation of what the surface magnetic field looks like through the chromosphere, with different colors indicating various strengths of the magnetic field. And so there's magnetic storms, and they shoot those hot gases out, and that's what gives rise to the phenomena that we see as flares or prominences or other activities. And so that structure that you're seeing, where there's a North Pole and a South Pole, and there's spicules and there's granules, flares and prominences, these are all phenomena driven by the magnetic field at the surface of the sun. I don't have which NASA mission or what mission took this shot here, but this is the chromosphere, and you can see loops, right? So magnetic fields, of course, don't generally not open. There's a North Pole and a South Pole, and so they're looping from one sunspot effectively acts as the North Pole of the magnetic field, another sunspot acts as the South Pole of the magnetic field, and so they loop between the two of them. So they're sort of like outlets for the magnet, or the anchor points of the magnetic field as you go in. So at last we reach the visible surface of the sun. It's called the photosphere. Temperature is around 6,000 Kelvin. Lovely shot here of an airplane going across the surface of the sun. And as we descend into this photosphere, we notice that the sun certainly has a lot of weather. And as we slip below the photosphere, that weather gets even more intense, okay? We're bounced around by incredible turbulence. We see spouts of hot gas going up, cooler gases cascading downward, and we are in what is called the convective zone of the sun, the convection zone. Okay, this is where energy is transported by mass motion, so it's bulk material moving up, bulk material moving down. It's turbulent, it's convective, it's a boiling pot of hot gases trying to cool off from the heat coming up from below. Okay, we've seen this image before. We are now in the convective zone. And if you look back a little bit, if you turn around with your spaceship and you look back up, you can see that the photosphere, which is now above you, simply defines the top of the convection zone. And so it's that convection that is the cause of that churning, bubbling appearance that you see on the sun's surface. So this is a shot from the Vacuum Tower telescope showing a sunspot, the structure around the sunspot. You see a lot of that flowery activity. We now know that's from the magnetic fields. They have origin points within the sunspots. And then around that, you get sort of this boiling looking appearance. White stuff is hot material coming up. The darker yellow material is cooler stuff that's flowing down. And so it's like a boiling pot of water where you've got flows going up and flows going down. About a third of the way to the center of the sun, the turbulent convective zone gives way to a much smoother, what's called the radiation zone. There's no weather here anymore. The weather's gone. We have survived the storms. We have survived the magnetic storms, the convective turbulent storms, where now energy is quiescently transported outward by photons. So this is another shot from NASA showing the structure of the sun. We've got our chromosphere, convection zone, and we're now into the radiative zone as we make our way to the core. Okay, and finally, we do plunge down to the core. The center of the sun, temperature is about 15 million Kelvin. The density is about 100 times that of water. So water has a density of about 1 gram per cubic centimeter. So the density at the center of the sun is about 100 grams per cubic centimeter. And this is where the energy of the sun is produced. This is where hydrogen is burned into helium. 4 hydrogen get converted into 1 helium, and the mass difference between those, E equals mc squared, is what drives the energy production in the sun. So when you have one of those nuclear reactions, so before we get there, I'll talk about that in a second. So how do we know this stuff? How do we know we're just not making this stuff up? It's a nice story. Do we have any evidence that's actually true? Sure. One way that we know about the interior regions of the sun, regions we can't see, is by watching sound waves bounce around. Kind of like very analogous to earthquakes. When the earth shakes a little bit, it sends off a series of waves, S and P waves, through the interior of the earth, and each of those waves has different properties and they bounce off material in different ways. And much the same is in the sun. You have sound waves that bounce around. Some of them make it farther in than others. That's what's shown in the image here. Some of them don't penetrate very deeply. Some of them penetrate much deeper, down near the core region. And so by taking a look at sunquakes, we can analyze those waves. By the way, the most common wave on the sun is about 5 minutes. So the sun sort of breathes in and out on 5-minute time scales as those waves bounce back and forth, that spherical cavity, as it goes through. And so we can learn about the interior, just like we learn about the interior of the earth from earthquakes, we learn about the interior of the sun from the sound waves that are bouncing around. And I kind of just said all that. This is what some of the data would look like if you looked at seismology in the sun. So it's called helioseismology when you do it on the sun. And you get these very distinct patterns. You get those patterns because it's basically a spherical cavity. And you get particular patterns that form when your box is not square, but your box is a sphere. And there's some actual data there showing how much power is in a given wave. So you've got a wave with a certain wavelength, and you'd like to know, does that wavelength have a lot of power or a little power? And that's what the data on the right is showing you. It's basically a power spectrum of the waves. Another way to study the solar interior is to observe particles that are called neutrinos that flow directly from the energy producing regions of the sun. So where those fusion reactions take place, you have 4 hydrogen converted into 1 helium. What comes out of that is high energy photons, gamma rays, and it also releases what are called neutrinos, little neutral particles, and they don't care about any of the stuff above it. They interact with matter very infrequently. They can penetrate light years of lead, and so they just go booming out of the sun. And there's a lot of fusion going on in the sun, so there's a lot of neutrinos coming out from the sun. And so by the time I read this sentence, roughly about 10 to the 18 solar neutrinos are going to go zipping through your body. But it's okay because they don't interact much. They just go bopping right through your body as though nothing ever happened. That alien-looking picture there is what a neutrino telescope looks like. Okay, so you're trying your darndest to try and capture some of those things that don't want to react. Occasionally they do, not very often, but occasionally, and you can try and capture those. So this is known as the Borax-Ino neutrino telescope, and they are trying to capture some of those solar neutrinos, which then, if you do capture them, they tell you directly about the conditions in the center of the sun. Here's another example of one. This is known as the Super K telescope. It's over in Japan. And what you're looking at there in the images are photomultiplier tubes. Thousands of photomultiplier tubes. And the guys are in the boat there because they're on water. You're actually seeing a layer of water on top of those that lower set of photomultiplier tubes. And when the telescope is operating, it is filled with water. Not any old water either. It's very clean water because you're trying to pick up very specific reactions. And so you need the water distilled and cleaned out of any impurities as you go. Okay, but that's what a neutrino telescope looks like, one of them. And so in that core, so the neutrinos go zipping out. We try and capture them. The other thing we can try and capture to tell us about the interior are the photons. So in the solar core, where we have nuclear fusion going on, you've got a freshly minted high energy gamma ray photon. And it doesn't travel very far before it runs into something. Usually an electron. It goes about 1 millimeter, not very far at all. And so it scatters, it collides with the electron, and that sends it off in a new direction, random collisions. And so the photon sort of bounces around in a rather haphazard way as it bounces from one electron to another. And every time it undergoes a scattering event with an electron, it exchanges energy with that electron, and it goes on out. And so these high energy gamma ray photons, by continually interacting, scattering, colliding with this other stuff in the solar interior, they slowly get transformed into lower energy. And so sort of the rule of thumb is that for every 1 gamma ray photon that you produce in the center of the sun, you're going to produce about 1,600 visible light photons. That's sort of the downsampling, if you like. So from 1, you get 1,600 visible light photons. And it takes about 1 million years for a photon to do a drunken random walk from the center of the sun out to the surface of the sun. And that's our journey from starting from Earth to the center of the sun and on our way back, where we capture a few of those 1,600 visible light photons that come out, which illuminate our blue dot. And that's what I had to say. Thanks. Okay. So I'm stopping mine, Tom. Hopefully I'm stopping mine. Tells me I'm stopping mine. There we go.
Okay, I'll see if I can get mine to show up again.
You know, on the other hand, I'm not. Usually, there's like a little window at the bottom where you can see yourself or see the other person. I don't see me, so maybe it's just me.
Okay, I'm not sure how you get that back.
I'm not either. I do something like that. I'm presenting to everyone. Stop. All right. Well, why don't you try?
ast. Oh, that was weird. Okay.
Okay, I saw the infinite regret.
Yeah, I think I clicked on myself, so it kept on showing. Oh, wait, I'm not sure. I wasn't sharing anything yet. Did something come up?
No, but it's not clear it's not me either.
You want to?
I wonder if I can just give you.
Show my.
How about if I let me try forcing the screen to you. All right, let's go over to here, control room. Get control room. Okay, I'm going to shut me up.
Yeah, it's odd. It worked before.
Try a screen share now.
Okay, is anything showing up?
Yes.
Okay.
Yeah.
And full screen?
Yes.
Okay, good. Well, it looks like we're good to go. Okay, so I'm going to follow up on the topic that I talked about the first time, and that was getting to know the night sky, what you should look for. And everybody is probably wondering what pieces of equipment they need to know the night sky. So I'll go through a recommendation on what you should look for in terms of using your own eyes, using binoculars, and using telescopes. So let's start with the human eye. And as we said before, that's best for constellations because they're so big. You need to see a wide patch of the sky. And if you use any type of magnifying device like binoculars or a telescope, you'll only see a small portion of these constellations because most of them are quite big. But the first thing you need to do is to get to a dark area away from city lights. And your eyes need about 30 minutes of darkness to really dark adapt. If you just come from your car with the indoor lights on or looking at headlights or your phone, your pupils will dilate a bit. They'll get smaller, and not as much light will be coming in. So and also your rods are getting excited with the white light, and they need a chance to settle down just a little bit. So so you find your dark site. It's good to bring a friend too, because so it's always good if you twist your ankle or something out there in the dark. You want somebody to help you to your car or get help for you. So it's always good to go with a friend. And once your eyes are dark adapted, you'll notice you can see a lot more stars in the sky. And some of the constellations have brighter stars that usually the stick figures get drawn about, and they'll start to look like some of the stick figures you see on your sky map. And that's another thing, is that you do need some sort of sky map to give you an idea what's going to be in the sky. And best way to do that is to print one out, go to a website that I'll describe later, print one out and bring a red flashlight, because red flashlights don't ruin your night vision like the white light of a flashlight. You can either buy one of those from an astronomy shop online, or you can put several layers of plastic wrap, red plastic wrap to dim the light. They'll work too. And let's see. And so once you've done that, go put a blanket on the ground or get a lounge chair and lay back and look at the sky and try and identify some of those constellations that are in your sky map. Okay, so that's the human eye. And let's see, the next page, the sky map. This is where you can generate a sky map for your particular location on Earth and for the time of night that you'll be going out. Because of course, as the Earth rotates during the night, you'll see the constellations either setting or rising, and generally moving across the sky, rising in the east and setting in the west. And why is it good to know what some of the constellations are? It's because there are some nice objects to look at inside these constellations, and you'll need to point your telescope at these objects. So if you have your star map and you know it's near one of the constellations, you'll look in the sky and see some of those bright stars of the constellation and sort of eyeball it as to where exactly you should point your telescope. But we'll talk a little bit more about that later. So this sky map here has has the constellations in there, but if you dig down deeper, you should see some of the more interesting objects such as globular clusters, nebula like the Orion Nebula, and some galaxies like the Andromeda Galaxy. And you'll want to know where to point your scope, which finder stars to use. Okay, so let's talk about the first purchase you might make, and that should be binoculars. And a standard pair of binoculars are usually listed as 10 by 50 binoculars, and maybe they'll cost you $50 for a decent pair. The 10 means the magnifying of the power of the binoculars, and the 50 is the diameter in millimeters of the primary lens. So let's talk about the magnification. For astronomy, sometimes too much magnification is bad because the field of view gets too small if the magnification is too high. And for binoculars, you want to use those for the large objects, so you don't want too much magnification. So 10 is just fine. And let's see, what about the 50 for the diameter of the primary lens? Well, the bigger that is, the more faint objects you'll see. But binoculars aren't really meant to be looking at faint objects. We'll leave those for the telescope. So it doesn't really matter if you get a 50 millimeter lens on your binoculars or a 70 millimeter lens. But once you get more advanced, maybe you would want to try your hand at some of the fainter objects. The drawback of a larger primary lens means it's going to cost more money and the binoculars are going to get heavier, which can be a problem if you're holding them up with your hands for a long time. So if you upgraded to, say, I hate to use the word upgraded, but if you got a more expensive pair of binoculars, like 15 by 70s, they would be roughly double the price, $90 or so. And it's also very important to hold your binoculars very steady. And to help you do that, you could get a tripod. An effective one might be $50. That would be stable enough. And with very stable binoculars, you can see the 4 Galilean moons of Jupiter in binoculars. But the key is the binoculars have to be held very steady, either on a tripod or maybe stabilized by holding it against the side of a building or the roof of your car. But it's pretty amazing what you can see just with binoculars. And if money is no object, you can buy a pair of image stabilized binoculars, such as the Canon 10 by 30 image stabilized binoculars, which are about 10 times the price of a normal pair of binoculars. For 50 new, 300 used. But if you want to spend the money on the image stabilized binoculars and money's no concern, you will definitely enjoy those binoculars more than the shaky ones at 10 by 50s. But that's the cheapest thing you could do to start your equipment purchase. Now, let's go to telescopes. Those are for the fainter objects that you would like to see. So the main factors to consider, let's look at the desirable features. You want it to have high resolution so you can see more detail, say pointing it at a planet like Jupiter or the moon, the craters of the moon, or even Mars. I've seen some of the craters on Mars in a backyard telescope. And you want it to be sensitive, meaning you want it to be able to see faint objects. If you want to see a galaxy, galaxies are not very bright, so you would like a telescope that has high sensitivity, which is gained by having a larger diameter mirror. And then the other thing is you want your telescope to be portable. You don't want to buy a 2-meter diameter mirror telescope because most likely it won't fit in your pickup truck or car. And even if you could manage that, can you lift it by yourself? So amateur telescopes are generally in the range, say maybe 6 inches to 24 inches, with, I would say, the most common diameter mirrors is probably about 8 inches. And the undesirable features are cost, weight, and size. And so you might ask, why not get the best sensitivity and resolution telescope? Because unfortunately, each of those improving sensitivity means larger mirror, which means heavier, bigger, more money, and same with resolution. So you want to you give yourself, how much do I want to spend on this telescope, and then you can decide what well, how much do I want to spend, and if I want to spend enough, will it fit in my car, and can I handle the telescope by myself or with a partner? So 2 practical types of telescopes to consider. One is the Newtonian reflector, normally in a Dobson style mount, which I'll show in the next slide. And generally that's the best performance for the money. And the next one is a Schmidt-Cassegrain style telescope. It's more expensive, but it's also more compact. And it has a mount that's a altitude azimuth mount, which is good for long exposure photography if your telescope has a motor-driven tracking system, which of course that costs more money as well. In a Dobson style mount, it's harder to track the sky, but it is possible. But the equipment to get a Dobson style telescope to track the sky generally cost about the same price as the telescope. So, okay, here we go. Next slide. I would say do not get a telescope that looks like these. They're touted as nice Christmas presents. They're pretty inexpensive, but I would claim that if somebody receives those as a present, they'll be frustrated very quickly, and it'll go in the closet and never come out again, and maybe kill somebody's appetite for looking at the sky. So there are a few things bad about these is that the tripods are usually very wobbly, and the mounts that connect the telescope to the tripod are very wobbly. When you're outside, you'll probably get some wind, maybe 5 to 10 miles an hour, and that wind can shake the telescope, and then you won't see anything very clearly. And generally it's a bad experience if you get a telescope that's under $100. Better to spend it on a good pair of binoculars. So what is a good telescope to buy? So we have a picture on the left of a Dobsonian style mount for a Newtonian reflector. This is for a 6-inch telescope, and you can see the price is roughly $300. One thing to note here is that this deal here does not come with eyepieces. Eyepieces can easily be $30 to $50 or more, but it does come with a nice flashlight. It comes with a star finding chart where you don't have to go to a website. You could dial it to the right time of the year and see what's going to be in the sky. So that's a pretty good price for a 6-inch telescope, and it doesn't have tracking, and it doesn't have an automatic go-to. You have to look through the finder scope and point it at the sky to find what you have to know where to point it to see the object. It's not computer controlled. And the one on the right is the Schmidt-Cassegrain style. Let's see. So the difference here is this one does come with 3 eyepieces, but the mirror is only 3.5 inches, meaning some of those galaxies might be pretty tough to see, but you'll still see the rings on or the cloud bands on Jupiter. You'll certainly see the rings of Saturn. You can see a lot there. And some people like this mount because you can align it so that it's let's see, the mount there on top. If you point that towards the North Star, it's easier to make adjustments so that your telescope will track the rotation of the Earth, and you'll be able to find the image you're looking at with just a quick adjustment. Because then, like I said, both of these are not motorized, meaning as the Earth turns, whatever you're looking at will move out of the field of view, and you'll have to inch your telescope just a little bit to find it as it moves. Of course, you can spend more money and get an automatic tracking system for the Schmidt-Cassegrain, and that will take care of tracking the object. On the Dobsonian one, you can't get a tracking system, but you can get some automation that will help you find the object you're looking for with some computer control. So it's definitely a trade-off in style, price, mirror diameter. So it can be confusing. So here are some of the pros and cons of each. For the Dobsonian mount, it's definitely cheaper than a Schmidt-Cassegrain. A 6-inch mirror versus 3.5, as we noted, the mount is definitely sturdier. It'll hold up better in the wind. And it's usually simpler to aim the telescope, I find, on a Dobsonian. Again, the disadvantages is that the telescope doesn't have a tracking mechanism. So if you wanted to take a picture, long exposures would smear the object, and it's definitely not compact. That tube can't be folded up. It somehow has to fit inside your car or van or whatever vehicle you use. Then with the Cassegrain style in the altitude azimuth mounts, the advantages are you can motorize it, and if you set it up properly, it will track the Earth rotation and your object will stay in view. And then that would enable long exposures, long exposures meaning maybe more than 30 seconds. I'm calling a long exposure anything longer than, say, 30 seconds. You might go 5 minutes, you might go 15 minutes. The scope is small and can be put in a carrying case. So if you don't have you don't have to worry about the scope fitting inside your car. And the disadvantages is it is less performance for the money, and the setup generally takes longer. And one other thing is that there are more surfaces that the light has to reflect off of and pass through. So some people find the same diameter mirror on a Schmidt-Cassegrain a little bit dimmer than that with just a Newtonian reflector. The common features to both of these are that you have a 1x finder scope, and those are included in the telescope, and that's essential for pointing. And by 1x means that there's no magnification. And that's extremely helpful when aiming. When you look in that 1x finder scope, you'll see a red dot or a set of concentric circles, and they'll tell you where the scope is pointing. So you move the scope around until that red dot is on the area that you want to look at. And that makes it a lot easier to find things. Now, some of them add a 10x finder scope, but if you only have a 10x finder scope, it's very difficult to find objects because you're zoomed in so close. You're not quite exactly sure where you are, and all the stars look bright in that finder scope. And it probably takes you 10 times as long to find anything if you can find it. But if you use that in addition to a 1x finder scope, then it could be a useful item, but you should not use that alone. And some telescopes come only with the 10x. So you have to make sure that it does have some type of a 1x finder scope. And magnification can be changed on any of these telescopes by just changing the eyepieces that you have. Low focal length eyepieces will give you a zoomed in view. Say the eyepiece is 5 to 9 millimeters. That's normally considered a zoomed view. And the higher focal length eyepieces will give you a wider view. And those are generally in the 20 to 40 millimeter range. And one way to help you find things is to use a high focal length eyepiece so you have a nice wide field of view. And you're looking in your 1x finder, you get it close, and then you can take the scope and move it just a little bit this way or a little bit that way, and your object should be visible. So once you center it on your object, then you can change the eyepiece to a lower focal length eyepiece and look at it in all the detail you like. And just a reminder, the magnification is given by the telescope focal length divided by the eyepiece focal length. And that, of course, the telescope focal length is fixed. That doesn't change, but the eyepiece focal length is dependent on what you put in the eyepiece. So you have control over that. And let's see, typical magnifications can run from, say, 50x to 200x or 400x. But once you get up to, say, 200x, many times the atmosphere starts to get in the way and the image starts to actually look worse in higher magnification. So you're not always able to use the full magnification power of what you have on hand due to atmosphere blurring. Okay, now, before you put money down on anything, I would highly recommend to go visit your local astronomy club. They usually hold monthly meetings where they meet with each other and give talks about their trips and what they've seen recently, or maybe some equipment they built. And on a different day of the month, they usually have a star party where members go and bring their telescopes and do observing of objects in the sky. And attend to the meeting and chat with the people about the pros and cons of their telescope. You can ask them why they bought theirs and what they like about it, what they don't like about it, and you can find out where they meet for their star party. Get directions, maybe carpool with somebody or caravan with somebody. You definitely don't have to bring any equipment to go to one of their star parties. But while you're out there, everybody loves to share the views of the objects in their telescopes because they think it's so cool that their telescope can see say the Orion Nebula and all the wispiness, and they're just dying to show somebody else what their telescope is showing them. And don't be embarrassed to ask them how much the scope cost. That's definitely not a taboo topic. And again, ask them what they like and dislike about their scope, or what they would do differently if they're buying one again. And after looking through the different telescopes and seeing their sizes, you'll be more confident that the scope you choose to buy is the one that you're going to be happy with. So that's my recommendation, and clear skies and happy viewing. And that's all I have there.
Cool. Thank you, Tom. Hey, have you ever actually looked through a pair of image stabilized binoculars?
Yes, I do. I do have those Canons.
Oh, you do? Okay.
Yeah.
Does it really work?
Yes, it's amazing.
Okay.
Once you have a pair like that, it's hard to use anything else.
Got it. Cool.
And of course, like everything else, Canon makes about 5 different sets of image stabilized binoculars, and I've got the one that has the widest field of view, which also helps in that it's the lightest version. They have some 15x binoculars with, I think it's maybe 60 or 70 millimeters of aperture. And there's the store in Tucson, the Starry Zona. On Friday nights, the owner brings out telescopes and lets you try out the different telescopes. And I went there once and asked them if I could try out the different Canon image stabilized binoculars too. And so that was pretty neat to get a firsthand feel of those. And so the other ones were just too heavy to keep on holding, so I went with the lighter ones.
Yeah, no sense having to get a tripod to hold your two heavy binoculars that are image stabilized.
Yeah, right.
What was that for?
Yeah.
Okay. We're 5 minutes over, but we're going to go just a few minutes more. We got one new question in the discussion board. So I will start that one off. And this question comes from Mike O'Ryan, or I don't know, maybe it's Mike Zero Ryan, who's watching. And he asks, I'm wondering why Mercury doesn't seem to experience the same sort of tidal heating from the sun that Io and the other Jovians experience from Jupiter. I'm guessing this could be because the eccentricity of Mercury's orbit has become so small that the squeezing due to gravitational change is essentially negligible. If this is so, then how have the Jovian moons maintained so much more eccentric orbits around Jupiter? Okay. Mercury does experience tidal flexing, tidal heating. So does the Earth. The tidal heating from the moon and the sun, just to give a sense of scale, the Earth's solid crust moves about 8 inches during tidal flexing. Io surface, on the other hand, flexes about the equivalent of a 30-story building. So the visible surface, the hard surface, or liquid perhaps, the entire land bulges. I mean, it's not a small effect. You will notice it. What was that movie? Interstellar, right? If anybody saw that, and they land on that one planet that was next to a neutron star, and time's flying by because of relativistic effects, and this planet has this amazing tidal force that goes around it. It's like a big wave going around the planet. It's kind of the same thing with Io. Not that extreme, but you know, moving the equivalent of 30-story crustal motion is pretty good size. Io is also larger, has a much larger tidal effect because it has resonances with the other Jovian planets. So it occasionally lines up with Ganymede and Callisto and Europa. And it's these extra resonances that help accentuate the tides on Io. On Mercury, Mercury doesn't have quite the same resonance structure with, let's say, Venus, Earth, and Mars that Io does with the other Galilean satellites. If I remember right, I'm going off the top of my head.
Uh-oh.
Okay, how much did I get cut off there?
I just see you. I think it was about 2 minutes.
Okay, I don't know what happened there.
Me neither.
I was yammering away and didn't look at the camera, and then I just noticed I was cut off. Actually got cut off twice tonight. That was the second time. I got cut off once when you were talking. So maybe it's just me. Maybe it's Google Hangout. Anyway, I will more fully answer the question then on the discussion board. But good question. Okay, I think that will do. So this is our last Google Hangout. So thank you very much for tuning in or watching on YouTube Live. And clear skies.
Bye now.
Bye-bye.